Hi everyone, welcome to today's tutorial on Best Science Brain YouTube channel. Today we are going to look at basic electricity 1, and this is a topic meant for students in SS3 and also people in SS1. But we're going to start from the introductory aspect meant for SS1 students before we now move to the SS3 aspect of this topic. If you are not subscribed to the channel, kindly subscribe by tapping on the subscription icon on the channel and get subscribed for once. So today we're going to start by describing what is meant by electric circuit. Electric circuit. You look at the board, you can see a circuit drawn on the board. So what is an electric circuit? Electric circuit is a path through which electric current flows. So the path through which current flows is called a circuit. So this diagram here represents electric circuit. So we have electric circuit. Electric circuit is a path through which electric current flows, and then this is the path through which electric current flows. And the diagram on the board represents a circuit which consists of electric cells, the key, the lamp, the ammeter, the resistor, and the voltmeter. Then these lines stand for the conducting wire. So the components of electric circuit, components of electric circuit include 1. The conducting wires, which I've described. 2. The electric cell. 3. The key, or otherwise known as switch. 4. The loads. The loads are the devices that draw current from the cell. Example of a load is bulb. They will have the electric appliances, which can include the ammeter, the voltmeter, and the resistor. So going back to the diagram, we have the cell, which provides electrical energy. We have the switch or the key, which controls current coming out of the amount of current coming out from the cell. We have the lamp or bulb, which is the load which draws current from the cell. We have the conducting wires, and then we have the appliances like the ammeter, the resistor, and the voltmeter. So that is electric circuit for us. It is a path through which electric current flows, and the components include conducting wire, the cell, the switch, the load, and the electrical appliances. So we now go to types of electric circuit. The types of electric circuit include, number 1, the open circuit. So what is an open circuit? An open circuit is a circuit in which electric current does not flow to the external wire or external circuit, and there is a gap in such circuit. So this let's go to the diagram there. You can see that this is an open circuit because the key is open. So the current is retained in the cell. So no current flows out to the external wire. What it means is there is no light on the bulb. The ammeter does not deflect, no deflection, meaning no current is coming out from the battery or cell, and the voltmeter does not deflect either. So current is retained in the cell. We call such a circuit an open circuit. Then the next type of circuit is called closed circuit. So what is a closed circuit? So this is a circuit in which current flows out to the external wire or circuit, and there is no gap in such circuit. So let's go back to our diagram there. So if this switch is closed, so that there is no space here, we now have what we call a closed circuit, because current will now start coming. I will now see the current direction, an arrow showing the current flowing out from the battery and returning back to the battery. So no space here shows that the circuit is closed. Current is coming from the battery. So we call such a circuit a closed circuit. Then the third type of circuit is called a short circuit. A short circuit is a closed circuit with no load. A closed circuit with no load is called a short circuit. For instance, you go to the diagram and remove the load, which is the bulb and perhaps these electrical appliances. So the kind of circuit we now have is now called a short circuit. A closed circuit bearing no load, only the key and the cells. So that's all about this circuit. Then we are going to the devices or the appliances we have in the circuit. So we are going to talk about the electric cells. Electric cell. Electric cell is a device, or there are devices that convert chemical energy into electrical energy. We call them electric cells. There are many examples. We have the dry cell, or I don't have the inclined cell. We have the Daniel cell. We have the voltaic cell. So these are examples of electric cells. They provide electrical energy in the circuit. Then in physics, the symbol to represent a cell is double parallel lines. Double parallel lines with one longer than the other. So they represent a cell. We have plus and minus polarity. So that's a cell. When I draw two or more cells in physics, two or more cells is called a battery. So a battery consists of two or more cells. Every cell in physics has what we call has a voltage called the electromotive force. The electromotive force in a cell. So, and also every cell possesses what we call internal resistance. Internal resistance. The electromotive force is defined as, which is also known as EMF, is the work done in taking, or we can say is the potential difference between the terminals of a cell when placed in an open circuit. That is the electromotive force, which is represented using E. Now the dry cell, or the one we use in our transistor radio, dry cell has an EMF of 1.5 volts. Two of it connected in series now give us 3 volts. While small letter R stands for what we call internal resistance, which is the resistance offered by chemicals within the terminals of the cell. So that is the cell which provides energy in a given circuit. Provides electrical energy in a given circuit. So that is the cell, and every cell, as we said, has an EMF, which is called electromotive force. Now, we're now going to look at combination of cells. How do combined cells in physics? Cells can be combined in series. They are called serial arrangement of cells. To arrange cells in series, we join them, we join the negative terminal to the positive terminal. So when we arrange cells in this way, joining positive to negative terminal, we say that the cells are in series or serial combination. Then we should know the difference between a cell and a capacitor symbolically. A cell, the two lines should not be equal to themselves, but for a capacitor, the parallel lines are equal to themselves. So we don't have to mistake a capacitor for a cell. This is a capacitor, while these ones are electric cells. So the lines are not equal in length. The capacitor lines are equal to each other. Now, having done that, we go back to the cell. Each cell has electromotive force, E, and also E. Internal resistance, they call this one E1, E2, and E3. Internal resistance R1, R2, and R3. Now, when cells are connected in series, how do we find the equivalent EMF or the net EMF? The net EMF is obtained by adding the total EMF of the cells. That is E1 plus E2 plus E3. That gives us the equivalent or the net EMF of the combination of cells in series. For instance, let's say we have this cell connected to another cell, plus minus, and they are each EMF of 2 volts. Total EMF now becomes 2 plus 2, that gives us 4 volts. So we get the net EMF by adding the EMF of the cells in series. So when you have 2 or more cells, we now have a battery. So these 2 make up a battery, while these 3 also make up a battery. So this is a battery of 3 cells, a battery of 2 cells. So we should be careful to note that when cells are arranged in series, we connect negative terminal to positive terminal, and so on. Let's look at this situation whereby we have a wrong connection. When we have a wrong connection, is when we have negative connected to another negative, or positive connected to another positive. We now have a situation called opposing EMF. Opposing EMF. So, for instance, if we have EMF here is E1, EMF here is E2. They are in series, but is wrongly connected. The net EMF will now become E1 minus E2, no longer plus, because they are wrongly connected. We now have what we call opposing EMF. For instance, we have this situation as equation. We have this. So when we have problems on cells, have to be very careful. We don't have to rush the equation. Be careful on the diagram. This is 10 volts, and this one is a cell of 6 volts. And we have to find the net or the equivalent EMF. It's not going to be 10 plus 6, because you look at the connection, that's the wrong connection. The shorter line goes to short line, or negative goes to negative. So the net EMF here would be 10 minus 6, giving us 4 volts. No, this is the wrong connection, no longer 16 volts. So let's take a problem now on another problem on serial connection. We have the problem that says 8 dry cells, each of EMF 2 volts, are connected in series. If 2 of the cells are wrongly connected, calculate the net or equivalent EMF. So look at the equation. 8 dry cells, each of EMF 2 volts, are connected in series. If 2 of the cells are wrongly connected, calculate the net EMF. So looking at this, to find the net EMF of this equation, there are 8 cells, and then 2 are unconnected. That means the number of, to find the net EMF, we use EMF of rightly connected cells minus total EMF of wrongly connected cells. There are 8 cells in this equation. 2 are wrongly connected. That means 8 minus 2 gives us 6. That means 6 are rightly connected. So the EMF of the right connected cells now be 6 times 2, since the EMF of each cell is 2 volts. And the total EMF of the wrong connected cell now becomes 2 times 2 volts. Since 2 are unconnected, that becomes 12 minus 4, that gives us 8 volts. So the net EMF of this arrangement is 8 volts. So this is a joint admission matriculation examination question. So having done that, we now move to the next way, the other method of connecting cells. As I say, cells can be connected either in series, then they can still connect them also in parallel. So to connect cells in parallel, we have the second method, parallel connection or parallel arrangement of cells. So parallel arrangement of cells. In this method, the cells are not connected end to end, no, but they are connected parallel to each other. We have this. Have another one parallel, so, and then another cell. They are parallel to each other. The wire coming out from each cell, they will all meet at 2 particular junctions. We have one here. So 2 junctions, here is A, here is B. So when you have cells in parallel connection, they have E1, E2, E3, or let's say 2 volts, 2 volts, 2 volts. How to find the equivalent EMF or the net EMF? When 2 cells are in parallel connection, the total or the net EMF is going to be 2 volts if they are the same. So when you have 2 cells that are the same, 2 or more cells that are the same, and they are in parallel connection, the equivalent EMF that represents all of them will be one of, just take one of the EMF to become the net EMF. One of the EMF becomes the net EMF. So if they are all equal, you take only one of it. But what if they are different? They have 12 volts here, 10 volts here, and 8 volts. They are different from each other. How to find the net EMF? When they are different from each other, the net EMF or the EMF is going to be the EMF of the cell that has the highest value. In this case, it is 12 volts. The EMF of the cell that has the highest value becomes the net EMF. So next, we are going to resistor, the next equipment or the next electrical device found in electrical circuits. So we are now looking at the arrangement of resistors in the electric circuit, the second component found in a circuit. Resistors are passive devices that oppose the flow of electric current. So every resistor has a quantity called resistance measured in ohms. Now different types of resistors, but the two major types we have in physics are standard resistors and variable resistors. Standard resistor is a resistor that has a fixed resistance. Resistor that has a fixed or constant resistance is called a standard resistor. In physics experiments, we can provide standard resistor making use of what we call resistance bus. Resistance bus can provide different standard resistor or different fixed resistances. Then the symbol for standard resistor is more like a rectangular bus with lines coming in and out of it. Then the next type of resistor is called variable resistor. Variable resistor is a resistor that has whose resistance can be varied or changed or altered. Example of a variable resistor is the rheostat. And the symbol is also like the other one, but with an arrow crossing it. Looking at the arrangement of resistors, just like cells, resistors can be arranged in series or also in parallel. So the first one we have on the board is serial arrangement, where the resistors are joined end to end. That is serial arrangement of resistors in a circuit. Maybe the result of this one can be taken as R1, R2, and R3. If I want to find the equivalent of the total resistance of resistors in series, I will add up their resistances R1 plus R2 plus R3. For instance, the situation we have this could be 2 ohm, another one of 3 ohm. And you have to find the total resistance. You just add the two of them together, 2 plus 3, that will give you 5 ohm. The next arrangement of resistors is, as I said before, is parallel arrangement. Parallel arrangement of resistors. In this one, the resistors are placed parallel to each other with their lines meeting at 2 points. We have parallel arrangement of resistors. That is this. We have this coming down there, coming down there. So they are joined at 2 points A and B. So current coming in the directions. Then we can call this one R1, R2, and R3. So when resistors are joined in parallel, how do we find their total resistance? We don't add them just like the way we add serial arrangement. We take the reciprocal formula. 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. For instance, if R1 is 2, R2 is 3 ohms, unit of resistance is ohm, R3 is 4 ohms, they are connected in parallel. How do we combine them? We take the reciprocal 1 over R equal to 1 over 2, 1 over 3 plus 1 over 4. We can now take the LCM of the 3 numbers, which is 12. 1 over R equal to 2 into 12 is 6, 6 times 1 is 6, 3 into 12 is 4. There, then this gives us 3. So 1 over R gives us 13 over 12. Now if you make R the subject, you invert both sides. R becomes 12 over 13 ohm, which is the equivalent resistance. So you see that when resistors are connected in parallel, they give lower resistance, and when they're connected in series, they give a higher value for the net resistance. So having done that, we have a special case, a situation whereby two resistors are, when you have two resistors connected in parallel, we can use a shortcut formula or a short method. So when you have two resistors in parallel, you may not start using 1 over R equal to 1 over R1 plus 1 over R2. That will waste your time. We can use a shortcut, which we can call R total in parallel becomes R1 times R2, that is the product, all over R1 plus R2, that is product over sum. R1 times R2 all over R1 plus R2. When you have two in parallel, you shouldn't go ahead wasting time looking for LCM. You can use this shortcut. For instance, if R1 here is 4 ohms. And R2 is also the same 4 ohms. So how can I find the equivalent? I'll apply this formula. R total becomes R1, which is 4, each of them is 4, 4. 4 times 4 all over 4 plus 4. Now that will give us 16 over 8. And that will give us 2 ohm, making the solution easier for us. So let's take an equation to illustrate another problem on resistors in parallel. I have this equation: 2 resistors of equivalent resistances give a net value of 2 ohms when combined. Determine the value of each resistance. So 2 resistors on the board over there, 2 resistors of equivalent resistance, that they have equal resistances. That's what it means. Give a net value. That means let the first resistance be R1, second one be R2. Since they are equal, it means that R1 is equal to R2. Can take the value to be equal to R. They have equal resistances. And then they give a total of 2 ohms when combined in parallel place. When combined in parallel, we are now asked to find the value of each resistance. So since the association of 2 resistors in parallel, we can use total equal to R1 times R2 all over R1 plus R2. Total resistance is the net, that is 2. R1 is taken as R. R2 is also R because they are equal to each other. All over R plus R. So when we solve this, we have 2. R times R is R squared. Then R plus R will give us 2R. So 1R value cancels 1 down. We're going to have left with 2 equal to R over 2. Cross multiply, R becomes 4 ohms. So each resistor is 4 ohms. This problem on the board, and we are asked to calculate the net resistance of this problem on the board. How to find the total resistance. So of this arrangement on the board. So look at the arrangement of the board. You have to find the total resistance. So some of them are in parallel while some are in series. So we'll start with, to make it easy for you, start with the ones in parallel. Let's start with this one, these 2 in parallel. So since they're in parallel, we can use the shortcut of using R1 times R2 all over R1 plus R2. Combine these 2. That gives us 2 times 2 over 2 plus 2, which is 4 over 4, 1 ohm. So when these 2 are combined, we get 1 ohm. Move on to the other set in parallel. That is 3 of them there. When I use 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. That's going to give 1 over 2 plus 1 over 2 plus 1 over 4. The LCM is 4. That gives us 2, 2, and then 1. So 1 over R equal to this. So 1 over R gives us 5 over 4. That means R is the inverse. R becomes 4 over 5, which is 0.8 ohms. So let's go back to the diagram. So we'll now go back. We'll now draw this, the first resistor, 2 ohms, already in series. Second one is 1 ohm. How did I get this 1 ohm? These 2 join together will now give us 1 ohm. Third one in series is 2 ohm. ohms. Then the fourth one is the other three combined in parallel, which we got as 0.8 ohm. Now total is obtained by adding all of them together. 2 plus 1 plus 2 plus 0.8. So when we add, we're going to have 5.8 ohms. So when you have an arrangement containing both parallel and serial combination resistors, first of all, join the ones in parallel and then treat everything as serial combination. We're looking at the next equipment, electrical device found in the circuit, the ammeter. The ammeter is used for measuring electrical current, and the symbol for ammeter is A in a circular, in a circle. So that's the ammeter in the electric circuit. Ammeter measures current. Then, if we want to measure small amount of current, we use the milliammeter, which measures a small amount of current. We want to measure a very small amount of current, very small or sensitive current. We use the galvanometer. So these are all instruments for measuring current. Now, what is electric current? We say in physics that current is defined as the rate of flow of electric charges. The rate of flow of electric charges is what we call current. And then current is obtained using, from this definition, per unit time, please, per unit time. Rate of flow of charges per unit time is current. So current is obtained using Q over T, where Q is charge expressed in coulombs, and T is time measured in seconds. Charge in coulombs. So the unit of Q, that charge is coulombs. We should also be aware that coulombs can still have some other smaller divisions, like microcoulomb. You have to know that 1 microcoulomb, this is microcoulomb, is 10 to the power minus 6 coulomb. 1 millicoulomb is 10 to the power minus 3 coulomb for conversion purposes. For instance, we are told that a current, or calculate the current flowing through a conductor when a charge of 2 microcoulomb was passed for 2 to the power minus 3 seconds. Find the current flowing through a conductor when the charge of this was passed through the conductor for this time. So these are charge. Charge is 2 microcoulomb. We'll convert to coulomb, which is 2 to the power minus 6. Since 1 microcoulomb is equivalent to 2 to the power minus 6 coulomb, then we'll have to bring it to SI unit or standard unit. So our time is 2 to the power minus 3 seconds, already in standard unit. So current is Q over T. Our Q is this, while our time is that. So 2 cancels 2. We apply the law of indices, 10 to the power minus 6, then this going up becomes plus 3. That gives us 10 to the power minus 3 amperes. Current is measured in amperes. So another device we want to talk about in a jiffy, apart from the ammeter, is the galvanometer. Is the voltmeter, sorry. The voltmeter. The voltmeter has this symbol V. The voltmeter measures potential difference in an electric circuit. The voltmeter measures potential difference in an electric circuit. So, what is potential difference? Potential difference is the work done in taking a unit positive charge from one point in a closed circuit to another. For instance, we come across a diagram of this nature. as we study electricity. This is the key, close, current is coming out. This is the ammeter, and then resistor, and then we have the circuit closed. Now, assuming I want to find the work done in taking a positive charge from this point A to this point B across the resistor, what I have to do is I'll attach a voltmeter across the resistor. So the voltmeter measures the work done in taking a charge of one coulomb, that is, unit positive charge, from point A to B across the resistor. That is the voltmeter. And then that work done is what's called the potential difference. To get voltage or potential difference, remember Ohm's law. Ohm's law says current equal to voltage over resistance. Make voltage the subject. Voltage, or PD as we call it, is current times resistance. Remember that this resistance is different from the small r. The big R is the external resistance offered by the resistors, while the small r is the resistance offered by the chemicals inside the cell. So the resistance we use to calculate the difference is the external resistance based on Ohm's law. Having done that, we'll now look at formula for obtaining current in a circuit. Formula for calculating current flowing in a circuit. Remember that the battery provides what we call the EMF. The battery provides the EMF, that the cell, the electric force of the cell is called EMF. And this EMF is given by the formula V plus Vs, where V is the potential difference measured by the voltmeter. Remember, I said that V is IR according to Ohm's law. Then Vs is called lost volts in battery. And that Vs is given by current times internal resistance. Look at the two formulas. Potential difference, or otherwise known as terminal voltage, is current times external resistance, while lost volt is current times internal resistance. Now, when we put these values into this equation, I have E equal to IR plus I small r. If you factorize, we have E equal to I into R plus small r. We make I the subject. I now becomes E all over R plus small r. So this is the formula for finding the current flowing out from the battery in an electric circuit.